Good morning, everyone. Welcome to the visualization recommendation session of IEEE VIS 2024. I'm very excited to watch all your talks today, presenting your newest work on kind of interesting ways of doing this in novel ways, coming up with good visualizations and good recommendations for visualizations. So I would say we get started right away. So our first speaker, Zhang, will talk about AdaVis, adaptive and explainable visualization recommendation for tabular data. And also be sure to ask your questions on Slido. So Zhang, the stage is yours.
Okay, cool. Can you hear the screen right now? Can you see the screen right now?
I cannot, yeah, now I can see it. Yeah, we can hear you and we can see your screen.
Okay, cool. Hey everyone, and here's Alex. And today I'm gonna introduce our work at AdaVis, adaptive and expandable visualization recommendation for tabular data. This work is collaborated with Haotian from Microsoft Research Asia and Huamin from Hong Kong University of Science and Technology and Wang from Nanyang Technical University. So imagine there's a boy, Alex, and he was given a table, and he need to consider what charts should be used for that table. And normally, what we can do, we can ask the machine learning model, which does the chart recommendation. So basically, the machine learning model will take the data set as input and output the suitable charts into a ranking list. So the machine learning model will guess how suitable each chart to the input table and then rank them in a descending order. In this case, the rank 1 means the line chart is most suitable for the table. Yeah. And also you can recommend the top 3 results, which means that the first 3 charts are recommended. However, the top end recommendation is problematic because it holds the assumption that the same top end can apply to different and various data sets. This means that regardless of the dataset characteristics, the machine learning model will always recommend a fixed number of charts, like some charts you are suitable for. Sorry. However, some datasets are good for 3 charts, while others are only good for 1 chart. So in general, the current specification lacks flexibility for the dataset characteristics. Yeah, optimally, the machine learning model should consider the table characteristics and recommend effective charts for the datasets. Here, we comes up with our research question. How can we design a system to recommend effective chart types based on characteristics in the data? So let me introduce our work AdaVis, which is a machine learning model can recommend effective charts according to the dataset characteristics. First of all, the table is an input is put into the model AdaVis, and AdaVis will determine the characteristics in the datasets, and then it will make recommendations for chart types based on these dataset characteristics. Which means that it also can recommend arbitrary number of charts which are effective to describe to the dataset. So here is the same. We are giving a input dataset, and in the recommendation, AdaVis will show its reasoning for that chart recommendation. Like here, there's a reasoning for this table. Like 2 columns of data are significantly correlated and fit a linear regression model. And then after exposing its reasoning, why these 2 chart, why, and then it will recommend two charts. And so basically the AdaVis will show its reasoning for the chart recommendations and then expose its reasoning why these two charts are recommended. And then these two charts are recommended. So to do the data set characteristic modeling, we extract 112 features from the data set. And here are some feature examples we use in the work, like the outlier, which determines number and percentage of liars according to different rules, and the missing values, the number and percentage of missing values, and also the statistical relationship, which describe the two data columns, their relationships, and also the data type relationships, which describe whether the two data columns are categorical and numerical. And here are more examples for different data sets. And these examples expose the reasoning of chart recommendations for three different data sets, like why the data set are recommended as a bar chart and line chart, or why the data set are recommended as a line chart and bar chart. Here, let me introduce the details of our method. So to train the model, we collect the dataset from Plotly Chart Studio, where people will upload the dataset and create charts. And then we use the MDLP algorithm to discretize the numerical feature into intervals. And then we select 4 commonly used chart types: line chart, bar chart, scatter plot, and box plot in our model training. And basically, we use 20,000 data set visualization pairs to train the model. And to model the dataset characteristic, we trying to work as a checklist. So as we have mentioned, we have 112 features, and then we will went through the features for that dataset to check its value. And in this way, we hope we can model the dataset characteristics from a comprehensive perspective. So here is an examples, like what's the number of unique values in a data column of the dataset? It's 200, and does the dataset column has missing values? And there's no missing values. And what are the two columns data type related? So these features can be categorized into two parts: single column features and cross column features. The single column features are features which describe one aspect of an individual data column in the dataset. Here, as you can see in the slides, the single column feature is like the length of the data columns. And also we need to measure another single column feature, like whether the data values in that columns are arranged in this order or not. Additionally, we will have the cross column features, and these features describe the interrelationship between two columns. Here, these two columns are numerical and numerical. After we extract the features from the dataset, we quantify them into the vector space by using the box embedding. Why we call the box embedding? Because these embeddings, they are like a hyperrectangle in the vector space. And so the advantage of the box embedding is that if the chart embedding are within the box, is considered as the recommended results. Yeah, since the box is flexible, where its location and size are changeable according to the dataset characteristics. Therefore, it can recommend effective chart types according to the dataset characteristics. Here's another example, like if there's only scatter plot inside the box, the model will consider the scatter plot is both for the dataset. But if scatter plot and line charts are both within the box, the model will consider the data set is suitable for these two chart types. And then we use an attention mechanism to assess the feature relevance to the final recommendation results. And then we build up a template, and those highly relevant features will be filled into the templates. Here in the bottom, we can see these are templates. And this field text is kind of exposure of the recommendation reasoning of AdaVis. Okay, let me talk about the evaluations. We did the ablation studies where we evaluate the results with and without cost column features. Cost column features is aimed to measure the two columns, their interrelationships. And as we can see from the examples, the feature, if we consider the cost column features, the the model can predict more appropriate chart types for data sets. The reason is because the data sets is need to measure their relationships. And then we also conduct the experiment to test our model's ability for multiple chart recommendations. And as we can see from the tables, our method achieve a group experiments when it can recommend multiple chart types. So let me wrap up our works. So our method allows the machine learning system to recommend effective chart types based on the table characteristics. To this end, we use 20 features to pop the table characteristics comprehensively. And we use box embedding techniques to enable the machine learning system to make adaptive chart recommendations. Thanks.
Thank you, Songheng. Well, a quick, brief question that was also asked on Slido. I think like for visualization recommendation, the one thing is the data, but the other thing is actually the user and the user intent. So one question is, how would your approach tackle this, that sort of like an appropriate visualization is also task and user dependent?
Okay, so right now that's a very good question. And in our user study, the users also asked me this question. So right now we didn't consider the user intentions. What we did is trying to find out all the available chart types for their data sets. And then to this end, we want to narrow the users their search space when they are deciding the charts. Yeah, I think it's a good next step for our next work.
Okay, thank you so much, Songheng. So next up is Wang, and he will talk about Draco GPT extracting visualization design preferences from large language models. Next up is Chen, who will talk about chart2vec, a universal embedding of context-aware visualizations. Jing, whenever you're ready, take it away.
Yeah. Hi, this is Chen. Today I'm going to present chart2vec, a universal embedding of context-aware visualizations. This is a collaboration work from Intelligent Big Data Visualization Lab of Tongji University and AntV team of the Ant Group. The recent advances in representation learning have prompted several studies in visualization community, and these studies attempt to use semantic vectors to present information from visualization data. For example, ChartSeer adopted an encoder-decoder approach that converts visualization to and from embeddings to assist exploratory visual analysis. And Li etc. proposed a structure-aware method to improve the performance of visualization retrieval by collectively considering both visual and structure information. These attempts to present visualization through embeddings can only be applied to one or two specific visualization tasks, such as visual comparison and visual recommendation. Moreover, most existing work is focused on the single-view visualization. And when we consider multi-view visualization, context information is a crucial aspect of this visual representation that influences the outcome of subsequent tasks. So in order to achieve a universal representation of visualization that can be used for various downstream tasks, we need to address the following three challenges. The first, we need to formulate the proper input embedding that leverages both semantic content and the structure information of each visualization. And second, a large-scale data set of context-aware visualization is required to form this training and test data sets. And third, we need to set up multiple deep learning tasks to learn the contextual information from a set of input embeddings. And these are the major contributions of our paper, including a high quality of context-aware visualization data set, and the chart-to-vec representation model, and finally, the key lessons summarized during the development and the design of chart-to-vec. And the specific implementation of chart-to-vec is divided into these 4 steps. We first do data collection and screening, and then data characterization and the formulation of chart-to-vec model, and finally the evaluation. Given the absence of this readily available high-quality context-aware visualization data set, we first collected the data set from various online platforms, and after screening and selection, we collected 1,098 high-quality multi-view visualization from Tabular Public and Calliope on 10 different data topics. And to learn a visual embedding, universal embedding of the visualization form from the declarative specification, we introduced this 7-tuple chart fact to establish this declarative format. And this chart fact is different from the previous from the previous presentation of Draco, since we have 3 levels of context from this chart fact type. One is elemental and encoded properly level, that is type of the chart. And then we have statistical concept relations that include the representation, the type of information described by chart fact, the subspace, breakdown, measure, and focus. And these are to describe the statistical concepts. And finally, we have the contextual and domain-specific insights. Okay, so for chart characterization, here I have an example. Consider the data set containing information about schools in the world, including columns such as school name, location, and the number of students. And suppose we generate a chart from the data set that depicts a difference in student number between rural area and urban area in Guizhou, China, represented as a vertical bar chart shown on the left. And the corresponding field of this chart fact are listed on the right here. So a chart fact contains both structure and semantic information. And then the fact schema follows a context-free grammar, which is a set of recursive rules used to generate patterns of strings. And therefore, the structure information of each chart can then be presented as a pause tray generated by a set of rules within this context-free grammar. And the fact semantics refer to the semantic content within the chart fact, including information from the data field and the value information. And here is our chart-to-vec model. You can see this from this end. This is input to the final output. And in order to capture information of a single visualization, we designed this chart-to-vec model, which consists of the input embedding here and the encoder. With the input embedding, it is possible to transform the raw data into a form that is able to be processed by the model. And after obtaining the initial vectors for both fact schema and fact semantics through the input embedding module, the encoder module employs 2 distinct operations, namely feature pooling and feature fusion, to achieve the final vector representation. And in input embedding module, the structure information from chart facts is encoded using one hot vector, while the semantic information is encoded using the word-to-vec model. And through this process, information from chart facts is transformed into computable vector forms through the two channels. And in the encoder module, feature pooling is utilized to capture semantic information from the data, and feature fusion is employed to reconstruct the correlation between structured and semantic information. And finally, feature transformation is applied for nonlinear transformation of the data to capture deeper levels of the chart information. And to better learn the contextual associations between charts, we adopt a multitask training strategy that combines supervised learning and unsupervised learning tasks. First, we employ the linear interpolation loss function for the 3 consecutive charts to establish the final vector that captures the contextual relationships. This is from the same data story. And to enhance the co-occurrence relationship, we employ the unsupervised learning task. By minimizing distance between the anchor and the positive samples shown in the orange here and the negative samples, charts appear in the same multi-view visualization can be brought closer together. And to enable the model to learn the spatial linear logical relations between multiple charts and cluster vectors located between the same multi-view visualization. To capture the co-occurrence relationship, we combine the above 2 tasks and use a multitask training strategy to optimize the proposed supervised linear interpolation loss and unsupervised triplet loss. And to assess effectiveness of this chart-to-vec model, we perform 3 experiments. Ablation study, user study, and quantitative comparison. So in the ablation study, we thoroughly investigate the significant and disability of each module. In this model, we perform the ablation experiments, concentrating on 4 aspects, that is training tasks, feature content, pooling strategy, and fusion strategy. And the results demonstrate that chart-to-vec achieves superior performance with this exact number here. And removing any of the tasks leads to a performance degradation. And in the second evaluation, we conducted a user study to validate the effectiveness of the chart embeddings generated by chart-to-vec. And this purpose is to assess the consistency of the calculated similarities between chart-to-vec and human perception. So we assess the final result with accuracy, which measured the degree of agreement between user selection and the model's calculation of similar charts. And this is a average accuracy and standard deviation. And this result suggests a high level of concordance between the model's calculations and human judgment. And finally, we conducted a quantitative comparison with 2 deep learning-based methods, which is Chart2Seer and Irado, to validate the performance of chart-to-vec embedding vectors in representing contextual information. And this is the exact number for the comparison. As shown here, all these findings demonstrate that chart-to-vec designed to effectively capture the contextual associations of the charts. In the discussion, we take a new perspective on the use of representation learning models to characterize visualization in order to learn the structural, semantic, and contextual information. And we conclude the limitations and summarize the key takeaways from the 3 perspectives, that is necessity of the context information representation model, customization, and fine tuning for visualization task. I will not explain in detail here. And we also have open sourced our code and also the data set, so you can access it on our website here. And thank you for listening.
Thank you so much. We don't really have time for a question, but maybe like a very quick one. So what kind of downstream task, did you have like one specific downstream task in mind when you sort of like designed and thought about this approach that you want to support, like maybe best in a way, and did you some tests on that?
In best ways, sorry.
Or like sort of, did you have like a specific downstream task in mind that you really wanted to sort of like excel at, where you really wanted to do well with your method?
Yeah, for example, this is a visual recommendation section. So one downstream task is a visual recommendation, but the difference between the previous recommendation methods is that this one can show the contextual information. For example, if you're making a dashboard or you're making a Tabular story, you want the system to offer recommendations, but it does not only show you recommendations of visualization or data which contain similar data content. It also can provide you with the recommendations from the context information and also the like the meta information. So this is different from some standard recommendation methods.
Thank you so much, Ying. We will now talk about agnostic visual recommendation systems, open challenges, and future directions, which will be given by Luca Podo.
Hi all. So, good morning to all of you. Today, I go through the presentation of our survey, which is the Agnostic Visualization Recommendation Systems, Open Challenges and Future Directions. So, our research question has been, what is a visual recommendation system but agnostic? We know that most of times when we have to deal with visual recommender system, the community and also the literature have already proposed different contributions in this direction. But recently, there is a new research branch within the VIS field that has emerged and basically is exploring this new kind of model, the exploit machine learning model for recommending visualization from a dataset, which are called agnostic visual recommender system. In this direction, we have explored in our survey the concept of the AdaVis. Initially, we have provided our definition for the AdaVis as a system based on a machine learning model that does not know which are the a priori, what are the visualization that can be produced from a dataset. And this kind of visualization are intended as visualization that can be insightful given that dataset, given the context where it is used for. So before to start, let's provide a little bit of background. In general, what a AdaVis is a system or a genius that we can consider at inference time that given an input a dataset or in general data, it is able to generate in output the most insightful visualization for that dataset. Obviously, this cannot happen without any kind of strategy behind. And there is something behind the hood that we have identified and we have explored, trying to provide the best formulation and also details about these new kind of models. So what we have defined as a crucial step behind the hood of AdaVis is the concept of the constraints. So meanwhile, the model is able to recommend the best visualization at different time, during the training time, instead, it should be provided with some constraint, with some guidance that should be used to identify and also the best visualization for the dataset, and also to learn which are the relationship between the data and the visualization that could come from a specific dataset. This concept of constraint will be explained in the next slides. So, in our survey, we have contributed with 4 different contributions: the Unfair4VIS service review, the AdaVis problem formulation, the definition of VRS constraint, and the AdaVis pipeline a state-of-the-art review. The first contribution is about the ML4VIS service review. We have initially collected the different surveys that have already been proposed in this field, where ML4VIS stands for machine learning approaches used in support of the different stages of the visualization pipeline. Here we have defined the 6 different dimensions. Based on that, we have compared the different We have compared the different surveys, and after that, we have built on our own. So if we want to summarize, the main difference between our survey and the other is basically that our survey focused specifically for the problem of the AVRS, provide a formal definition of the problem of AVRS, and also provide the ML pipeline that would be required for generating and for training an AVRS. Differently from the other is that explore and focus more on studying how machine learning approaches could be used in the different stages of the data visualization pipeline. The second contribution is regards the AVRS problem formulation. As I said at the beginning, the idea is that you provide a data set and you get an output the most insightful visualization. But this happens, but how is it possible? So we have to start from the data set D. We know that the dataset then consists of a set of features, where the features represent the different column of the tabular data that are used for this kind of approaches. Then we know that we should pair the different columns to get all the possible combination of columns pair that could be used for generating 2D visualization. It is important to notice that not all the feature pairs are valuable, because there are some that, for example, ordinal to ordinal pairs would return not valuable results in terms of data visualization. For this reason, it is important to select the subset of feature pairs that will be valuable for this task. After that, we introduce the second ingredient, the constraints. As I mentioned before, the constraints are some guidance that is used during the training phase to drive the model toward a very specific direction while suggesting the best visualization for the dataset, and also learning the relationship between the data and the visualization that we propose. So these ingredients are proposed to the AVRS that is trained, and after that, another ingredient is necessary, which is the insightfulness measure. Even if the model can produce different visualization, not all of them, even if they are correct, will be insightful for that specific dataset. So it's important also to tune and to introduce the concept of the insightfulness measure to let the model learn how to rank the different visualization we produce to return the first, which is a subset of all the possible visualization that can be generated from the dataset, initial dataset T. So I've talked about constraints, but what are these constraints? The constraints, we have defined 4 different constraints. One is the syntactical one, which are mandatory, and the 3 others that are optional and can be used in an overlap way during the training phase, which are the perceptual, the task, and the design constraint. We have also identified an hierarchy in the definition of this constraint, where the syntactical one are the crucial and are mandatory to be respected by all the AVRS. The other instead could be used to improve in this based on the scenario or the context where the model will be used. So let's go step by step. Syntax constraints. These are the constraints that every AVRS should take in consideration while suggesting a visualization. And because it has to respect the different rules for the different visualization that could be proposed. For example, if you consider line chart, we know that there are some specific column types that could be used on the different axes. And the model should know that and should master these rules for all kind of visualization to not produce not correct or not valuable visualization. Then we have the optional one, the one that can improve based on the scenario when the model will be used. The task-based basically would develop the model toward a very specific property of the relationship between the data and the visualization. For example, to the model could be tell that it should learn better the relationship between data and visualization to show trends, the most insightful visualization for trends in data. After that, we have the design one. The design are about the aesthetic to beautify the visualization. There are some cases where the aesthetic of the visualization is important. Sometimes it is not mandatory to be considered, but in other cases, for example, if we consider maps or other aspects, they start to become crucial. And these involve, for example, appropriate layout, the right color, and scaling, the grid, and so on. And finally, the perceptual one. The perceptual instead are the constraints that the model should learn when suggesting a visualization, whether there is some specific pattern that should be highlighted and enhanced before to be delivered to the user. Like, for example, if there is a trend, the model should be able to enhance the property of the trend in the visualization and then deliver it to the user. Finally, the last contribution of the paper discussed in this survey is the AVRS pipeline. Obviously, it is a machine learning supervised system, so it requires a training phase where the data sources are represented by data visualization pairs that are providing input to the model along with the effectiveness measure and the constraint that can be used then to train the model and generate the predicted plot compared to the ground truth, and then they are used to have to fine-tune and to train the model that would return us the model knowledge. The difference time is that we just propose, as discussed at the beginning, a data set, and then the model should be able to produce a list of a ranked list of the most insightful visualization based on the scenario of the training phase to the user. So included in the also investigate all the different contribution that has been proposed in this field, and we can notice that this field is relatively new, with the first contribution that has been placed in the 2018. So this marks an important point for this branch, which has a lot of space for contribution and also a lot of challenges. To conclude, the main opportunity of these approaches are basically that they can allow to democratize the data visualization and support the decision process of the user in analyzing data, in analyzing data set or more in general data. Moreover, they would help to avoid the cold start of what to analyze into a data set. The challenges that are about the definition of the effectiveness measure or the effectiveness properties of the visualization, because this is a problem that does not accept a unique solution. And so it's a complex and tricky problem to be solved. And the other one is that obtaining high quality data set for training this kind of models. So I hope you enjoyed the presentation. I'm here to answer your question. I'm Luca Podo from Sapienza University, and here you can find the QR code for the full paper. Thank you.
Thank you so much, Luca, for your presentation. Unfortunately, our schedule is a bit tight, so we don't really have time for questions. So be sure to check out this card if there are any questions from the audience. So we move on to the next speaker. Vaishali Dhanoa will talk about detour, semi-automatic generation of interactive guided tours for visualization dashboard onboarding.
Yes.
And we can see your screen and can hear you.
Perfect.
Thank you. Take it away.
Hi, everyone. I'm Vaishali Dhanoa. I'm doing my postdoc at the Aarhus University, Denmark. And today I will present our work that I worked on during my PhD at the Johannes Kepler University Linz and Proto Future, along with collaborators from TU Vienna, VIS, and Aarhus University. Well, as my work is based on dashboards, I would like to point out that dashboards are routinely used in public domains and in industry to make data-driven decisions. And our research community has also highlighted the use and the challenges that come with using these dashboards in practice at nonprofit organizations and uncountable number of businesses where they rely on dashboards on getting their work done. And Sarikaya et al. In their call to action questioned, everybody is using dashboards, but are they well prepared and supported? And I'm guessing that you might have also had to explain these dashboards to your end users after creating them at some point. And perhaps you would have, to explain these dashboards, perhaps you would have created a programmed interface for a step-by-step tutorial, or actually given a presentation or recorded a video, or maybe written a documentation or something else. And in our previous work, we created a process model that formalizes these different ways of onboarding and emphasizes the need of having an onboarding loop alongside the dashboard usage loop. And in our current work, we create the onboarding system for the authors such that they can create these custom interactive tours for the users so they can onboard themselves on their dashboards. So for clarification, we refer to onboarding as the process of introducing a new dashboard to the user. So imagine that you are the author of the sales dashboard, and now you need to explain this dashboard to a user who is a salesperson. So you might start explaining by one of these 2 key performance indicators, then a filter, and maybe at least one of the visualizations on the left, and then on the right, and the global filter. And to identify what needs to be explained in the dashboard, we systematically broke down each aspect of the dashboard. So starting from the KPIs, where we have the data, what transformation it went through, what insights you can gain from it, and how would you interact with the filter, and for each visualization, what needs to be explained. And for a seemingly simple dashboard, this can be too much. And then we have the connection between these visualizations due to the inherent interactive nature of the dashboard. And explaining all this information to the user might confuse them, especially if they're new to the dashboards. And this is what we observed in our previous work and in our experience with actual end users, especially for novice users. It can confuse them if they're not properly onboarded on the dashboards. So far, we have discussed the challenges in using the dashboards and how onboarding can potentially help. And now we will discuss the challenges in creating and onboarding for a dashboard. So while for the authors, it can take them too much time to prepare this perfect onboarding, as it might require significant knowledge, such as how to write a perfect onboarding documentation, or the technical skills required to record a video or create a programmed interface, or perhaps have an online meeting or in-person meeting with individual users to answer their dashboard-related queries. And for the users, based on their knowledge, these onboarding experiences can be confusing or make them not interested and unengaged if they are experts. And so to address this challenge, we created Detour. So like a detour can lead you to unexpected but enlightening path and back again. Our approach, Detour, guides users through the landscape of data visualization, allowing for both structured learning and free exploration. And it also supports authors in crafting these tours semi-automatically. So consider our previous sales dashboard. Now imagine that you need to explain this to a manager and to an employee. Without Detour, you might be scheduling in-person meetings with both of them. But with Detour, you can create tours that start with the dashboard's overall purpose. From there, you can explore specific charts interaction, which fits the needs of the employee, and then only explain high-level insights, which fits the need of the manager, and then maybe end with a common topic on how to gain insights from this line chart. So apart from this structured exploration, your users can also do a free exploration at any time and onboard themselves at their own pace. In addition to the world of storytelling and onboarding, we also draw inspiration from open world video games where we have a start and an end, and the main quest that help players to progress towards completing the game. And there are also side quests that support but do not necessarily advance the story, such as in the case of Skyrim, a well-known open world video game. So what does it mean for Detour? Consider the structured exploration I presented earlier. For an employee, this interaction branch will be their main quest, but they can also choose to onboard themselves on the other branch as a part of their side quest. And for the managers, it would be the other way around. Apart from this structured exploration main quest, the authors can actually also create groups in which they can put together a bunch of visualizations and then make the users go through all of them, only one of them, or at least one of them before moving on to the next step in the tour. So with this inspiration, we can use Detour for crafting and using interactive tours for dashboards. For authors, it means creating interactive tours with ease, adapting them based on users' needs, and publishing and sharing them with the users. For the users, it means they can view and use these interactive tours and adapt the content as they please, and then switch to a free exploration at any time. We implemented this approach using the Detour prototype. So for the authors, this prototype takes a given dashboard and automatically extracts its content and allows the author to either use already crafted tours or manually arrange them. You can also explain each of these visualizations here using a text, which is generated automatically, or in recorded audio or a video. And then you can finally see the crafted tours in real time. For the users, for a given dashboard, they can choose a path, which is indicated with the green frames around visualization, and then adapt the content using less or more details as they please, and then opt for a structured or free exploration at any time. So this is how the prototype for the authors looks like. We are using Microsoft Power BI dashboards, which are widely used in the industrial settings. So essentially, we can take any Microsoft Power BI dashboard with default visuals and create an onboarding experience for it using our prototype. So the content from the dashboard is extracted automatically here on the left side. And then in the middle, we have the space for crafting these tours, either manually or by choosing a template from one of our default templates. And then here on the right side, we basically have the possibility of viewing how our tours look like. You can also set the level of the user as you perceive based on their domain or VIS expertise, which then automatically adapts the content present here in the text box. So this is a fast-forwarded video to explain how our detour prototype works, how you can use it for crafting onboarding experiences for the end users by dragging and dropping the visualizations from the left to the center and connecting them as you go. And once you're satisfied with the result of the prepared onboarding, you can publish and share it with your end users, who can then start the onboarding tour and interact with the dashboard, as well as the other information that you have provided in your onboarding experience. For example, here we have a video, and a user can actually play the video and interact with the dashboard at the same time. We evaluated our work with actual dashboard users who regularly create and onboard their users who are actually domain experts. And as they use Microsoft Power BI, we could easily take their dashboards and use our detour prototype for crafting onboarding tours. So we had 5 authors who regularly create dashboards, and each one of them shared their real-world dashboards with us, which resulted in 5 dashboards, and then we presented them to their users who were mainly domain experts but new to the dashboards, and 2 of the users were actually new to the company. With the authors, we spent 1.5 hours in which they created these tours for the end users. And the authors, for example, commented that using detour might reduce the training time of their colleagues, and they found it easier because they could guess 90% of the questions that the users might ask in advance due to the automation. As for the users, we had a 10-minute session where they onboarded themselves using our detour prototype, and they said that the interaction with the dashboard alongside the onboarding was very convenient, and they found the more or less detailed option quite helpful. In conclusion, we present detour, a novel approach to onboarding users on complex dashboards and supporting authors in creating onboarding tours semi-automatically. And it also provides flexible learning paths for users of all expertise levels. Thank you very much.
Thank you so much, Vaishali. So I'd like maybe one question. So I guess the way users in your system can sort of learn about the interactive part in a dashboard is by providing a video that sort of like the authors have to provide, right? Or is there a way of also maybe thinking about ways of integrating this demonstrative like interactivity within your workflow and framework that sort of like this is actually applied to the actual dashboard visualization?
Yeah, we also thought about that, but due to the fact that we're using embedded dashboards, it's currently, we couldn't do it technically, but this is definitely the next step to actually have in-person or in-place animation so that you can see directly how things work.
So Jay Stokes has a question about that. He says, like, very interesting. How is the explainer text created? What features of the chart does it cover from the initial design space outline?
Yeah, so in the paper, we basically describe the component graph in more detail, where we explain how we break down every component of the visualization and then how we create these text based on the information that we get from each visualization. Was that the question, right? Yeah, so this is explained more in detail, and then we actually abstract the information in 3 steps. What's the general information that needs to be presented, what's the insight that needs to be presented, and the interaction information that needs to be presented to the users.
Okay, and maybe one final question. How about adding analysis goals and tasks to the onboarding path for novices instead of just giving them freedom to explore?
Yeah, we also thought about that, but I'm not sure if this already goes a little bit in the direction of guidance. So that's why we wanted to stick more to onboarding. And if we address the concerns of guidance, maybe we will as well look into that.
Okay, thank you so much again. So we will move on to the last talk of this session, which will be given by Chen, and it is about manipulable semantic components are computational representation of data visualization scenes. So Chen, whenever you're ready.
Hi, can you hear me and see my
Yes,
slide?
hear you.
Cool.
Yeah.
So hello everyone, I'm Chen, a PhD student working with Professor Zhang Liu at the University of Maryland. I'm honored to be here presenting our paper, Manipulable Semantic Component, a computational representation of data visualization things. Many visualization tasks, including interactive authoring and editing, chart animation, visualization, reverse engineering, and chart content navigation for accessibility, requires a suitable computational representation, the format and methods that define how a data visualization thing is represented and manipulated within a computational system. Examples include bitmap, vector graphics, and program. Consider visualization image processing in modern convolutional neural networks, where the format is bitmap and the methods include convolution. Bitmap images are usually easy to collect, but as many as rectangular arrays of colored pixels, bitmap cannot be easily adopted to support interactive tasks such as chart authoring and editing. As for SVGs, different tools introduce inconsistent SVG element types and structures. Here are 3 SVGs from 3 tools for the same group bar chart shown on the left. We can see that mascot is using rectangle elements, while the other 2 are using path elements, and all 3 have different mark grouping hierarchy. Then how about programs, code snips that generate visualizations? There are different types of these program languages and toolkit. First, declarative grammars such as Velardi conceal the thing structure and do not provide native support for directly referencing, selecting, and editing this thing object. Thing assembly languages such as D3 allow us to directly select and manipulate thing object, but they are hard to parse and lack high-level semantic abstractions. Furthermore, it is difficult to generalize solutions developed for one single language to other languages and libraries. So researchers have been proposing new representations of visualization things, but mostly task-oriented. Here's an example from the chart reuse system, where the authors proposed 2 mark structures and 6 scene update operations, however, only for reverse engineering and reusing infographics bar charts in PowerPoint. As a result, a unified and expressive data-based computational representation that generalizes well to a wide range of tasks has been missing. To this end, we propose a new computational representation called Manipulable Semantic Components, aiming at support visualization, thing understanding, and augmentation. To give it an overview, MSC is a continuous effort led by Professor Liu since fall 2020. Taking a graphic-centric approach, MSC treats graphical objects as first-class citizens and focuses on how they can be created, modified, and joined with data. Conceptually, MSC has 2 major building blocks: a unified object model describing the visualization thing structure in terms of semantic components, and a set of operations to modify the thing components so as to update the visualization. Let's use this stack bar chart example to show which shows the result of a survey in different age groups of people to illustrate how MSC describes the visual structure and generative process of this chart. Here is an overview of the thing structure of the example with the MSC representation. It contains reference groups, including the axis and legend, and the main chart area consisting of texts and colored bars. The main chart area has several major semantic components, such as marks, including rectangles and texts, groups that specify the nested collections of the marks. For example, here, rectangles are having a 2-level grouping horizontally then vertically. Layouts, the spatial relationships between objects within each collection. In this chart, each row is stacked, and the vertical layout of rectangle groups is grid. Encodings, visual channels of marks that are representing data. Here, the width and fill color of rectangles and the text content of text marks are encoded. And lastly, constraints. In this chart is alignment of the bar groups between agree and disagree response types, and the affix behavior of text onto the corresponding rectangles. The 5 components together define the semantic structure of the stack bar chart example. MSE can synthesize the VIS object of the stacked bar chart example using its generative operations. For example, we first create an initial rectangle mark, then repeat it with the age data attribute, resulting in gridded 4 rectangles. Then each rectangle is divided using the response data attribute, resulting in 4 rectangle collections. Each single rectangle now represents 1 response type for a specific age group. After that, width and fill channels of rectangles are encoded with the percentage and response data attribute. Further, the 4 groups are aligned between bars representing the agree and disagree response types. Finally, texts are created and affixed to their corresponding rectangles. Here's a complete overview of all the components and operations in the MSE framework. In the example we just showed, we saw how generative operations like repeat and divide can modify the VIS scene. In the next example, we will show how the repopulate operation can be used for chart repurpose. The repopulate operation regenerates visual elements inside an existing collection based on a new attribute in a new dataset. Here in the example, the attribute's country is replaced by months, and MSE will automatically read the distinct values and reflect on the new set of marks. Apply encoding operation can be connected with repopulate to repurpose a chart with new data. In the later application section, we will see a more complex example illustrating the power of MSE. We also have the stratify operation to generate layered representations of hierarchical data. Here we show stratifying a rectangle and a circle that result in an icicle plot and a sunburst chart, respectively. Due to time constraint, we cannot cover all the components and operations. Our website contains detailed descriptions to all the APIs and many chart demos. Feel free to explore. We demonstrate the benefit and generalizability of MSE through 3 downstream applications. The first one is interactive with authoring, where we use MSE to build a new version of Data Illustrator. Here is a demo video of creating a Nightingale's Rose chart. The operations such as repeat, divide, and apply encodings are represented as manipulation widgets in the UI. Compared to the old version, the new Data Illustrator is much more expressive and compact. More examples are on our website. The second application we explore is interactive chart repurposing. Current approaches, including D3 deconstructor and chart reuse, are limited to specific charting tools and chart types. With MSE in hand, we achieve reusing tool agnostic SVG charts, which is demonstrated by a system called Mystique that was published in VIS 23. Our system Mystique will first infer the X and legend areas and allow the user to inspect the results. Then the system decomposes the main chart area into a MSE representation. In the reuse UI, Mystique uses the MSE representation to prepare a series of guided data mapping steps on graphical objects and visual channels, each of which will reflect a repopulate, apply encoding, or apply constraint operations in MSE. The guided process allows the user to repurpose bespoke visualizations like this tree map group bar chart with just simple interactions. The third application we explore is augmenting animation behaviors for static charts. Animation authoring tools oftentimes have requirements on their inputs. For example, the system we consider in the paper called CAST requires so-called DSVG charts, where additional data datum attributes are synthesized for marks encoded with data. However, the DSVG generation tool provided by the authors only works for charts from Charticulator, Vega, and D3. So to unlock animation for general SVGs, we have achieved a unified script to synthesize DSVGs as long as the MSE representations are present. Here is 4 demo videos of animation by CAST on 4 different MSE represented charts. No matter where the chart comes from, with the help of its MSE representation, animation by CAST can be made possible. To summarize, MSE is a computational data VIS scene representation. There are 2 major parts: a unified object model describing the VIS structure, and an operation set for manipulating the scene components. MSE is evaluated through 3 applications: chart authoring, animating static charts, and child deconstruction and reuse. With that, I would like to thank my advisor, Leo, and the other author, John. I'm happy to take any questions.
Thank you so much for your presentation. So one question I have is like the space sort of like from sort of like what you see is what you get, authoring tools, like also like the commercial ones like Tabular, and then that's already huge, but then there's of course also like the programmatic approach, the coding approach, and then we also have the declarative grammar languages in between, sort of like where do you think sits your approach like in that spectrum of sort of like what you see is what you get versus the coding approach?
Yeah, that is a great question. So I think so the different approaches are actually having different levels of abstractions. So as for the coding, for example, in the D3, it can be very tedious, and it won't for the APIs in D3, you will need a very low level coding expertise. And for the system where like fits a scenario of what you see is what you get, it's more like an intent-based authoring. So usually the abstraction level there is pretty high, and you just need to specify intent using simple interactions. However, we would like to achieve an abstraction level somewhat at the middle. So it still has a power of it still have the expressiveness that is that is some benefit from sort of rooted in a program language, but still we also want to allow our representation to be able to produce high-level APIs for the user to interact with. So that results in the different set of applications I just shown. So yeah, it's really about like which level the representation is at and what is the benefit of being at that level.
Okay, thank you so much. So let's thank all of the speakers of today's session again. And be sure to check out the remaining sessions today and tomorrow at VIS 2024. Thank you for watching and see ya.